So I would like to give a broad but brief account of the research that we have at the University of Pisa and in Pisa more globally about the topic of human-centered AI, actually grounding this discussion on a large national initiative that is called FAIR. FAIR stands for Future AI Research. It's a large nationwide project funded by Next Generation EU, so the resiliency funds from EU. It's a large initiative funded with more than 115 million euro globally, organized into 10 spokes that are distributed across the country and coordinated by a central hub. In Pisa, my university is coordinating the first spoke of this partnership that is precisely entitled Human-Centered Artificial Intelligence. And myself and Francesco Marcelloni are the coordinators of this activity that overall has as main partners, together with the University of Pisa, who's the coordinator of the spoke, the National Research Council, which has a large establishment in Pisa with two large computer science-oriented research labs, and the Scuola Normale Superiore, the Italian branch of the École Normale Supérieure in Paris, together with two large companies that are part of our activities. Intesa Sanpaolo is a European-wide banking company, and Deloitte, the consultancy company. I would like, first of all, to give you an idea of the scientific objectives that we pursue within this project, and what do we mean by human-centered artificial intelligence in terms of our past and ongoing experience in many research projects and networks of excellence that were developed in the last 10 years to develop this idea of human-centered artificial intelligence in Europe, that is essentially the study of AI systems that cooperate in a synergistic way, in a proactive way, with humans at collective and at individual and collective scale. Now, the key point is to develop a form of hybrid intelligence, hybrid human and artificial intelligence blended together, so that we can amplify human intelligence, human cognition, instead of replacing, with a focus on maximizing the benefits of this human AI collaboration, while preventing, predicting, and possibly mitigating the associated risks that are always, as we were discussing previously with the previous presentation. So the key adjectives that we bind to human AI ecosystems is being adaptive, collaborative, responsible, interactive, and co co-evolving. The ability that the human users and the AI systems have the ability to co-evolve towards expressing ever more intelligent hybrid cognition. And clearly, the key point is that the design of such systems should leverage human strengths and compensate for human weaknesses in a context that is socially and ethically and legally informed, that is based on the respect of fundamental human rights, and the ability of people to maintain their agency, autonomy, while interacting with AI systems. And this is not simply, let's say, I would say, a motivating framework, but it's really the the context in which a lot of technical challenges emerge for developing the next generation of artificial intelligence systems. So as I said, one of the key aspects is how to enhance rather than replace human intelligence in complex or high-risk decision-making tasks, like, for instance, in healthcare. How can we provide meaningful interfaces that between AI systems and, for instance, dermatologists, doctors that try to make a diagnosis in a way that the system is not simply predicting or recommending a certain diagnosis, for instance, or a certain outcome, but rather it also provides explanations for the guess. And for instance, is one of the systems that we developed in the project is able to provide, given an image for a skin lesion that needs to be classified and characterized, the system is able to use predictive and generative AI tools to provide prototypes, examples and counterexamples of skin lesion with similar or different classification in a way that the decision of the dermatologist can be as informed as possible in order to be precise, and especially in, of course, in the cases where the classification is less clear, rather than obvious. So from this point of view, it is important to design systems that are aware of their own limitation, especially when they are somehow handling specific cases where there is a low confidence, and it is particularly important, for instance, to prompt the human user with the information that this specific instance is a difficult one, is a dubious one, and help reason about why it is so low confidence in order to first of all capture the attention of the human decision maker, and second, to provide tools for the human decision maker to make more informed decision as possible. So from this point of view, we are committed to develop hybrid decision-making systems, taking into account the specific aspects of the characteristics of human cognition, which is typically our reasoning in decision-making goes with two levels. So Kahneman's system 1 and system 2 minds that we have. System 1 that is fast, intuitive system to make instantaneous judgments, and system 2 that is instead our rational, deliberative reasoning part of our mind, which is much slower. We tend to use it very, very little. 97% of the time we use system 1. We use system 2 only when system 1 fails, or we are prompted with a situation of increased risk. So we need to understand how we reason so that we can develop what we call thought partners of humans, that are able to interact with us at the proper level of system 1 and system 2 in order to create a fruitful collaboration that it is able to co-evolve by this mutual influence that goes over and over again in the evolution of the system. This is a project that is now in the third year. It actually the end of it will be the end of this year. And when it started in 2023, it was, coming together with the two great game changers, the generative AI and LLM revolution that has amplified opportunities and risks of artificial intelligence in general, and it's also has created a kind of paradox, because these systems are able to interact with us with a very much human-like manner, providing indistinguishable human-like contents with different modalities. But this does not necessarily mean human-centered, because of course this human likeliness comes with a lot of problems in terms of being able to, while predictive AI is able to provide a level of confidence of the suggestions provided, generative AI has not this possibility. So it opens a lot of questions on how to have it trustworthy, responsible LLMs, for instance. And the other big game changer is the arrival of the European Artificial Intelligence Act, which is the first systemic law of the AI market globally, and which also opens a lot of questions on how to define systems that get all the opportunities offered AI within a legally compliant framework. So this is how we framed, in this context, we framed our research questions, along these three lines of the lines of human-centered machine learning and reasoning, how to design models, AI systems that interact synergistically and continuously co-evolving with people. And number two, how to tackle this issue, not only at the level of small teams or individual users, but to societal scale human AI ecosystems, like what we observe in large platforms like social media or e-commerce and e-marketplaces or LLM platforms. And third, the responsible design of trustworthy AI systems, how we can develop a meaningful way to responsibly co-design, develop, and validate, and use and monitor during usage trustworthy AI systems. And we are doing this also within an extensive set of experiments, case studies, and pilots that are helping to stress the ideas that we are bringing forward. I would like to use the remaining time to give you an overview of the main line and the main outcomes that we have along this line. So we have a work package that is devoted to explainable AI as a support for this synergistic human AI collaboration. We are looking at it both from the point of view of how to explain black boxes like deep learning models or generative models by treating them as black boxes with post-hoc explanation. But also we are developing ways of designing AI systems and models that are interpretable by design. They are constructed in such a way that they deliver their outcomes together with an explanation of their reasoning. We have a task where we pursue the cognitive aspects of explainable AI for hybrid decision making, and also how to somehow take into account of decision theory to design the explainable AI interfaces, also looking at user studies that allow us to understand what are the different options and how performing are the different options in providing hybrid intelligence. Now, hybrid intelligence is really some new important aspect, and we need to somehow, first of all, measure, understand, and possibly foster by designing appropriately interfaces so that this cognitive fruitful interaction between machines and people takes place. Just a quick point. We have as an important outcome of our project. We are developing a large platform, comprehensive platform for explainable AI by integrating and making available under different interfaces, both methods that has been for explainable AI that has been developed within our project, but also beyond, also state of the art. And we are also conducting project with our colleagues. We have expanded the partnership with cognitive scientists from Università Cattolica in Milan that are designing and performing together with us a large user study to understand the impact that explainable AI and learning to defer systems have on user. Defer is precisely, as I was mentioning before, a new strand of machine learning model that are able to understand when it is better to defer a decision on a specific case to the human counterpart. And explainable AI mixed together with this defer machine learning models are a new frontier for human AI collaboration. And we need to understand what kind of effect these tools have on the user's ability of doing hopefully better decision making together. We have a second work package that is now somehow focused on reasoning about system 1 and system 2 from the machine point of view. No, also machine and AI models can be, let's say, organized into a system 1 strand, which is typical of neural models and deep learning models, and system 2 models, which instead provide symbolic representation for learning and reasoning. And this work package is centered on neurosymbolic system that are able to mix in different, according to different approaches, the neural and the symbolic part, possibly within an explainable approach, so that we can bind this to the previous explainable AI approach. There is also strong interdisciplinary work in this work package with mathematical and physical colleagues that are trying to understand also what mathematical structures may improve our understanding of learning dynamics and how machine learning works. We have a focus in a third work package on human-centered lifelong learning. We need to somehow to have novel ways of continuously having socially and environmentally intelligent models that are able to continuously adapt to the evolution through the interaction with humans. So here we focus very much on more advanced form of continual learning, continual interaction, coevolution, also in reference to structured domain like graph neural network. One line of activity here is how to provide explainable graph neural network model. But another focus here is on large language models, multimodal language models, how to have cross-modal and cross-lingual learning to improve the trustworthiness of language models. You will see next a highlight by my colleague Alessandro Lenci, who will be presenting an outcome of this strand of activity on developing benchmarks to validate the reasoning abilities of multimodal language models. As I said before, we also want to have a human-centered AI applied not only to individual user or small teams, but also to in the entire societies or large societies. So we want to understand blending AI with complex systems. We want to understand how we can model society scale complex human AI socio-technical systems like we observe in many platforms of different kinds today, because we are interested in understanding the social and economic impact of this AI assisted socio-technical system. If we think today, what are the most popular and the most pervasive AI tools that we use, the answer is essentially the recommender system that we find in the different platforms that we use for social media, social networking, e-commerce, and the like. And understanding better the social and economic impact of these systems, it is really important, both from a theoretical point of view, but also from a practical one. We have here a lot of multidisciplinary work with our colleagues from the social sciences, from economy, and from, for instance, human geography. One outcome that I would like to emphasize here is this work on human AI coevolution, that is a new lens through which to look at the trajectories of mutual evolution of human behavior and platform effect in large platforms, how humans and AI influence and adapt to each other over time. This is a paper that recently appeared on artificial intelligence, is provoking a lot of discussion around the scientific community. And it is centered on how we can make models of the human AI feedback loop, because in platforms like, for instance, social media is an example, but there are many others actually. AI tutoring system for education can be another example, but many more. User choices determine the training data on which recommenders or AI assistants are retrained or fine-tuned or whatever. This will provide suggestions that will influence users, that will, or in turn, will provide novel, new training data that will be used to retrain the next generation of recommenders. And this is a perpetual loop that we need to understand better if we want to understand the outcomes of AI, different approaches to AI recommenders that we can find over platform, and understand better their impact on society. Just to make one concrete example, using this kind of methodology, we were able to show through digital twin simulation that the current generation of car navigators that that of course follow a feedback loop like this one have the somewhat surprising effect of increasing the concentration of traffic on the same few roads. It is possible to show that the more people follow car navigation recommendation, the more the traffic and the pollution is concentrated on a smaller number of roads, which is an example of undesired societal outcomes of this form of coevolution that prompts for new ways of designing maybe the next generations of recommenders to avoid these drawbacks. The fifth work package is about decentralized cooperative learning. This is actually co-chaired by Francesco Marcelloni, and you will see next a highlight by Francesco on federated learning of explainable AI models. Again, here is to tackle the effect of learning from different distributed or decentralized architectures. So to see also from the point of view of learning how we can scale our ideas to as decentralized as possible architectures. We have a work package on co-design methodologies for trustworthy AI systems that are compliant by design to applicable ethical and legal standards. The point here is to make concrete operationalization, implementation of ethical values and legal obligations, so that we can design trustworthy by design AI system. We have actually a startup lab called Good AI Lab that we founded as an offspring of this work. And we also have produced courseware for PhD level programs that we are experimenting currently in our national PhD program in artificial intelligence that are specifically designed on how to design responsible AI and responsible generative AI systems. So I hope I was able to give you an overview of our main approaches. We also have a final, very important work package where we perform empirical studies and pilots of human-centered AI system in a very broad way. We have, this is just the long list of different pilots and demos and concrete use cases that we are bringing forward. This is really important because it allows us to work with our multidisciplinary colleagues in a very effective way and in a very, let's say, intense multidisciplinary sense, not only with our philosophy and law colleagues for the aspects related to ethics and the AI Act, but also for just to make one example of many with our archaeologists that are developing together with us a human-centered AI system for the classification of archaeological items, for instance, and explainable AI help the archaeologists to perform the classification work. But this is just one example between many. Let me conclude by telling you that this is a large multidisciplinary effort. The formal members of the team are 39 multidisciplinary scientists from University of Pisa, Scuola Normale, and National Research Council, coming from 9 different departments. So not only engineering and computer science like Francesco and myself, but also colleagues from, for instance, linguistics like Alessandro that will be speaking next, philosophy, geography, jurisprudence, law, economics, social sciences, 2 different CNR institutes, not only science, but also social sciences from École Normale Supérieure, and 2 institutes of National Research Council. We have hired quite a number of researchers, PhD students from the National PhD in Artificial Intelligence and postdocs that were hired on the project. And we have been broadening the FAIR partnership through cascade calls with which we funded 6 new projects for basic research with academic institutions, 3 projects with our FAIR companies, Banca Intesa and Deloitte, and a very ambitious cascade call for small and startups and that are right now performing 11 different projects in collaboration with us. These are the new academic partners. I mentioned Università Cattolica for the cognitive science part, but also we have the other Tuscan University, Siena, Firenze, Scuola Sant'Anna in Pisa, and Scuola IMT in Lucca. And as I said, 11 new industrial partners, small companies that are really interesting startups developing, helping us to concretize our ideas. Also, from a scientific point of view, I didn't mention bibliographic references, but we really have a huge scientific production. Up to now, you see more than 100 journal publication, most of which in top quality journals and conferences. We run regularly a yearly workshop on human-centered AI. We just had our last March. Really colorful, refreshing, deep diving in cutting edge human-centered AI. 2 full days, 130 participants, many presentation and of the different kind. I can tell you, it is a blossoming ecosystem that is growing in size and complexity, showing impressive advance in a relatively short amount of time, both from the point of view of methodologies and use cases, and the multidisciplinary cross-fertilization is actually taking place. Final add to say that we are now brought a lot of effort in organizing the 4th edition of the Hybrid Human Artificial Intelligence Conference here in Pisa. It will take place very, very shortly from 9 to 13 of June. This is just an ad if you are interested to participate or send your students and collaborators. There's a very rich conference program, 5 days of program, 2 pre-conference workshops, tutorial, doctoral consortium, and an artificial intelligence and art exhibition, and 3 days of main conference with the keynotes session, interdisciplinary panels, poster and demo session. The session teams, as you see, are really connected with our scientific program, so human AI collaboration and hybrid intelligence, ethics, trust, moral reasoning, human AI interfaces and interaction, explainability, perception and decision support, societal impact of AI, adaptive system, attention and diversity, and generative, creative, and user-centered AI. We have a fantastic keynote speakers. You see, we have Stuart Russell from Berkeley, Ricardo Baiza Yates, John Shaw Taylor, and Jonathan Stray from Berkeley again. So this is just a commercial ad, and thank you very much for your attention.
Thank you very much, Dino, of course, for the presentation, but also just as a guide of this very big project that we have at the University of Pisa and in general at Pisa, because as you described, it's not only the University of Pisa involved in the project, but other institutions really in Pisa. And you mentioned the official numbers, but I think that's more than 200 probably researchers are really involved in this book, in the research activity on AI from different perspectives. And this is, I think, it's the strong point of this collaboration that we have active in Pisa at the moment. So I just, as I remembered before, you can write possible question in the chat if you want just to really do some questions, but I think that we can just leave the floor to the next presentation, and then we will discuss a little with possible question among the panelists and questions from the attendees. So I leave the floor to Alessandro Lenci.
Hi, Can you hear me? Yes.
Yes, the presentation is a native Italian challenging dataset to test the reasoning abilities of multimodal language models. And please, Alessandro.
Good morning, everybody, and I'm very happy to be here. And as Dino was mentioned before, I'm a computational linguist, and I direct the Calling Lab, which is a computational linguistics laboratory at the Department of Linguistics here in Pisa. But I have a strong collaborations with the Department of Computer Science, with Dino, and the Department of Computation Engineering with Francesco. And I'm also part of the FAIR project that Dino was talking about before. In particular, my group, and here you can see some of his members, in particular Lucia Passaro and Alessandro Bondielli from the University of Pisa, have been working on WP3 of Spoke 1, namely investigating language model and multimodal language modeling. Especially also developing research in order to test their linguistic abilities and also developing, as in these cases, new benchmark in order to get a better understanding of their competencies, both for the linguistic part and for the multimodal part, namely language and vision. And what I'm going to talk about today is exactly this, the first outcome of this research, which is actually a joint work with other members of the FAIR project in other spokes, in particular Bernardo Magnini from FBK Trento, Raffaella Bernardi, Uni Trento, and now Uni Bolzano, Davide Testa and Giovanni Bonetta and Alessio Miaschi from the CNR. So it's a big group that also can show how different spokes in the FAIR project can also be very connected on, let's say, transversal problems like the one of research on large language models. Okay, in this research, we have built a new data set for a new benchmark to test and analyze the multimodal language model for Italian. You know that the multimodal language models are extremely important nowadays in the new landscape of generative AI. And in these cases, we focus, most of the work still has been focusing on images. Now here we're going to we focused on video analysis. So this is actually a benchmark in order to understand a multimodal language models working on video data. We wanted to develop a benchmark that is native Italian, namely that focus on video that depicted Italian situations, Italian typical events or landscapes or cultural events, because we wanted to focus on the testing on the new generation of multimodal model for Italian language. Some of them, it's just native Italian language model are just arising in this recently, but there is a lot of research focusing on exactly developing and using and trying to see and to develop and test models that are native for the Italian language and culture. So in this benchmark that we have called Maya, we collected from YouTube 100 videos that depicted different type of typical situation with Italian culture and with different type of topics, places, food, sport, people at work, Italian landscapes, Italian art, typical events. You can see here, for instance, a video about the Siena Palio or pizza making in Naples. Also because, there are already very important data benchmarks for video language model analysis, but they all focus on English culture. While we know that these models are also very sensitive to cultural biases, and we wanted to have something that reflected closely Italian culture. Each of these video has a length of 30 seconds, and there are all Creative Commons data that in order that we can release. Then it started a very intense and very let's say important effort of let's say data augmentations, in the sense that for each video we identified 12 semantic categories of reasoning, because we wanted to test also to have a benchmark that allow us to carry out a fine-grained analysis of which type of information, which type of reasonings were more challenging for state-of-the-art model. And I will show you these 12 semantic categories in a moment. And then for each category, we use crowdsourcing in order to collect Italian questions and answers about what is happening in the video. So we asked, first of all, we ask crowd workers to provide 2 questions for each category for each video, collecting in total 2,400 questions. So these were questions belonging to the different semantic categories I told you before. Then for each of these questions, we ask other crowd workers to provide 8 answers to each of these questions. And this allowed us to collect 90,200 question-answer pairs. As a last step, we also wanted to generate foils, namely false statement about the video, in order to be used for control the actual ability of the models to discriminate between true and false statement about the video. For this type of task, we use a language model, use GPT-4o, and we ask the model with a prompt to generate a true and a false statement, so a foil for each video and each question, and these data then were manually checked for their quality. So in this sense, it's a real example of this human-computer synergy that also Dino was mentioning before about the human-centered AI. This is just a snapshot of the different semantic categories. So for instance, you can see here a video of a person making a pizza. And here are all the semantic categories. For instance, the causal category asks questions about the reason of doing something. So why is mozzarella melted? So he asked the question is asking the cause of some event. That's the correct the answer provided by one of the crowd workers. The heat from the hood oven has melted it. So it's the correct answer, the correct cause, which was then turned into a true statement. Mozzarella is melted by the heat of the oven, and paired with a false statement with the foil, mozzarella is melted by the heat generated by the sun, which is used as a control. Okay, so in green, the true answer, the true statement, and in red, the foil, the false statement. And you can see here different type of semantic categories of reasoning. For instance, the counterfactual category focus on things that might have happened, but they were not actually depicted in the video. So for instance, the question is, what would have happened if the pizza chef dropped the pizza on the floor? So it's something that is not actually depicted in the video, but is related to the event that is depicted in the video. Other relations on the other categories focus, for instance, on spatial relations or temporal relations or planning of different sequence of actions and so on. And these will allow us to make a fine-grained analysis of what are, let's say, the strengths and the weaknesses of the current model, because we know that these models do not perform evenly across different type of reasoning type. Okay, we use this data in order to define 2 tasks. The first task is let's say, is a closed task. It's a visual statement verification task. So basically, the model is provided with a question, with a video, with a question, and then there are two options: a true statement that depict something true about the video. So the young people are dancing because there is a DJ set, and then there is the foil. The young people are dancing because they made a bet. And the system has to choose which is the correct one, which is the true one with respect to the video. The second task, it's harder, and it's an open-ended visual question answering. So basically, the model is provided video, a question, why are the young people dancing? And the model has to provide the answer to this question without any type of, without any other cue. So in these cases, these are, for instance, these are actually the 8 answers that were provided by the humans. So this is our gold reference. And actually, the model answer is compared with the gold reference in order to see whether the model answered correctly and consistently to the question. Okay, we have done some preliminary work using different type of state-of-the-art model on the 2 tasks. So again, task one is the statement verification one. Task 2 is the open question answering task. And it's interesting here that, I mean, first of all, the second task, task 2, is much more complex than task 1. Which meant all the models, the performance of the models drop consistently and significantly with respect to the previous task. And that's interesting because in a way, the first task 1 is a classical lab task. Okay, so it's something that we do in a laboratory in order to test the models. But actually, if we look at how these models are used in real applications, well, they will be actually used in an open setting like this open domain and open question answering set. So the fact that this model, performance of this model drops significantly in the second task give us the idea that there is still quite a lot of work to do in many areas. And another interesting thing is the fact that the performance are not evenly and not equally for the different type of categories of reasoning. And also, what is interesting is that we compare the model performance. So the 1 frame and 32 frames refers to the multimodal models, namely models that can access both to the visual part and to the linguistic part. On the other hand, the black video settings is one in which basically we provide the model with a blurred black image in order to see what was the performance of the model only relying on the linguistic input. So basically, it's a kind of baseline that we use in order to understand to what extent this model really rely on both visual and linguistic information. Because we know from other research that there is this kind of, let's say, multimodal reduction in the sense that in some cases, model need to resolve a multimodal task, but actually only exploit linguistic information. This means that they still are not able to exploit also the visual information. And it's interesting that, for instance, for some categories, these models are able to provide, to perform very well, only relying on linguistic information. While in other cases, for instance, for spatial reasoning, we see that only the true multimodal setting is the one that allows the model to achieve significant performance on this type of task. So what we learned from these first experiments that, well, our benchmark Maya is quite challenging, which means that still it is important, it's interesting and useful in order to test the model's current limits of the multimodal video models. And also that again, these models are still not really able to address in a satisfactory way certain aspects of reasoning. So are very good, very well performing for certain type of reasoning, but still, I mean, the gap with the human performance is still quite significant for other areas of semantic inferencing. So we have been writing a paper and submitted to a conference, but you can also find the paper that described this data set and these further experiments on arXiv. And where there are still, I mean, there are a lot of work that we're still doing on this data set, improving and making also more sophisticated error analysis. We also want to try to see also to test the models not only in this type of general ability to, for instance, answer correctly to a statement or to a question, but also, for instance, to identify correctly where the entities that are mentioned in the questions are actually located in the movie, in the video. So let's say testing also the models with respect to their object detection ability. And of course, we are still working in our group in order to, again, understanding what is the division of labor between the visual part and the linguistic part in this multimodal model. Thanks.
Thank you very much, Alessandro. And we are a little late, and I will try just to go fast for the next presentation. In any case, again, if you have some question, please put the question in the chat in such a way that I can read the question and obtain some reply. I just give the floor to myself for the next presentation, and I hope that you can see the slide. And I will try just to introduce very fast the federated learning of explainable AI, just to introduce very briefly this work that was developed inside the FairSpoke one, and inside also other projects that we are in particular in my department. I want to start mentioning the AI Act, because in the AI Act, in the first sentence of AI Act, we find that the AI Act was proposed to promote the uptake of a human-centric and trustworthy artificial intelligence. We talked about human-centered AI. Dino just described what we are doing in terms of the subjects in the Spoke one of FAIR, but we are working a lot also trustworthy AI, and in particular I'm very interested in really presenting the Act at the beginnings, because this is also offering an opportunity just to describe how we arrived at the Act. In particular, the path towards the Act began in 2019 with the publication of the Ethics Guidelines for Trustworthy AI by the European Commission High-Level Expert Group on AI. Why I found these guidelines very interesting? Because inside these guidelines we have really some aspects that are technical aspects, but some other aspects that come from laws, come from ethics, and so on, come from society. And in particular, in these guidelines, we can find these 7 requirements towards trustworthy AI. I just put in orange 2 of these requirements because were the starting point of our work just concerning federated learning of explainable AI models. In particular, one of the requirements was privacy data governance. The need to collect data to train accurate AI models clashes with need to preserve privacy of data owners, and the other was really the transparency in which we have that the AI system and their decision should be explained in a manner adapted to the stakeholder concerned. Just putting together these two requirements, we introduced some years ago the idea of federated learning of explainable AI models. This idea was selected as key innovator by the European Commission Innovation Radar. But what is the idea? The idea is just to explore, on the one side, the federated learning that was introduced to cope with the privacy of data. In the federated learning, we just don't use to move the data in a server or in a client and to really execute some machine learning with all the data available, but we move models or the aggregated information from the client towards normally a server, and we have just an exchange of this information in such a way that we don't move the raw data, but we exploit the information that we have in the single clients to create a global model with these global potentialities. This idea of federated learning was really introduced by Google some years ago, and is the basis of the Gboard of Google. But today, in the scientific community, this idea is really very, very much investigated. Just to give you a glimpse of what we can do with the federated learning, this actually is an example in which we use as a model neural networks with the same structure, and each client just train these neural networks locally with the local data and transfer the model to the server. The server just aggregate the different neural networks by creating really a global neural network with the same structure, but by using as weights a weighted sum of the weights received by the single nodes. In this way, we don't move data, but we exploit all the knowledge we have in the single clients. But this actually was the initial proposal for really the federated learning by exploiting neural networks. But we know that neural networks are normally considered as opaque models. If we want just to really also cope with transparency, we have to introduce also the idea of explainability for this federated learning. And in this perspective, we started to think about explainability just in the field of federated learning. And in particular, when we talk about explainability, we can cope this problem from two different perspectives. The first perspective is to design inherently interpreted models, for instance, rule-based system or decision tree. On the other side is to exploit post hoc explainability techniques. This means that we can generate a opaque model, and we can try to explain the behavior of this opaque model when we receive an instance that we have just to classify, for instance. In terms of interpretable model, we can use decision trees or we can use normally rule-based systems. In terms of decision tree is just directed a cyclic graph in which each node reasons on a value of specific variable, and just considering the specific value we have in the variable, we can just follow one of the paths that are output from the decision node. In this way, we can arrive just to a leaf, and in the leaf, in terms of classification, we have the class, or in terms of a regression problem, we normally have a linear combination of the input variables. But I don't want to enter into the details of how decision tree just works. I want just to give you a glimpse of what was our solution just to have a federated decision tree. In the previous slides, I just showed that we used a fuzzy federated tree, but we can apply this idea also a classical decision tree without introducing the fuzzy theory. The solution we proposed is very interesting because preserve the privacy and produce the same trees as applying the algorithm to the joining of the local data set. So in other words, if I consider all the local data in all the clients, I just put together this all local data, creating really a global data. If I apply the traditional decision tree learning to this global data, I obtain exactly the same decision tree as I can obtain by exploiting the algorithm we proposed in the paper that you can see in the bottom of the slide. The approach just consists in iteratively the transmission from the clients of aggregated data to the server, which uses this information to select the variable for the next decision node in the global tree. So in this way, just in an iterative way, we can generate the global decision tree. These just are the results we obtained in different data set. With FL, we consider our federated learning solution. With LL, we are considering the local learning, means that the use only of the local data for the single client. With CL, we consider the centralized learning, the approach we introduced before when we can create this global data set. We can see that the federated learning approximate very, very well, of course, the centralized learning. Another possibility, I told you before, is just to use also a rule-based system. In this slide, I'm introduced fuzzy rule-based system, but the concept is the same also if we use classical rule-based system. And in terms of federated learning, we just proposed a solution for which each client just using the local data can learn a rule-based system. These rule-based systems are transferred from the client to the server, and the server just apply a method to really create a global rule-based system, of course, solving possible conflict in the rules and just to try to reduce as much as possible the rules. In this case, we don't have an iteration between clients and server, but we have just a transfer from the clients to the server of the rule-based system generated in the clients. These are the solutions we just proposed in terms of explainability with interpretable models. But I just told before that we can have also post-hoc explainability, and probably one of the most popular techniques we can really find in the literature is shape. Shape just attribute these shapely values that quantify the impact of each feature on a model prediction. When, for instance, we have to classify a specific instance, just using the shapely value, we can really have an idea of the impact of each feature in this model classification. And this, of course, can be very useful to explain how really the model is working. I don't have too much time just to describe our solution, but I want just to transmit to you what is the difficulty to use this sharp post-hoc explanation when we are in a federated environment. To really compute the Shapley value, we have to use the background dataset. This background dataset is normally just the training set we are using for creating the model. Normally, it's not really the training set, but we use some samples of the training set, or we apply some clustering algorithms to find some prototype of the trainings. This is due to the complexity of these approaches, for which we have to reduce as much as possible the background dataset size. But what is interesting, when we have to cope with a federated learning environment, we don't have the possibility to use the training set because the training set is in the single client. So if we use this training set, we will have as a result that each client has a different explanation with respect to the model. So our idea was just to create a way in such a way that all the clients have the same explanation about the global model. How this is possible? This is possible because we used another idea that we proposed last year, just to have a federated clustering approach. If we have a federated clustering approach, we can just find prototypes, but without moving the data, we can extract some prototype of the local data set we have in the single server. By using these prototypes, we can create a background data set that is common for all the clients without, of course, just forcing the privacy. This enables us to really provide an explanation by using the Shapley values that is consistent in each client. This solution just allows us to ensure consistency, ensure accuracy, and of course, just enforcing the preservation of the privacy. These are some of the results we obtained in terms of explanation, without entering in details because we don't have time, but you can really have the idea that actually the explanation we can provide by exploiting this approach are very similar to the explanation we can obtain by using all the training data in the way that we join all the local data in a centralized way. Of course, this solution is not possible if we have to preserve the privacy, but normally we use just to compare our solution with the centralized approach. Of course, this federated learning of explainable model was proposed. We are investigating more about the possibility when we have non-independent and identically distributed data. We would like just to cope with federated learning with streaming data. And of course, we won't just investigate more about hyperparameters and just to propose solutions in other fields. We just talked about a data set with a number of instances, but would like also to explore also the possibility to use federated learning, for instance, for object detection or image recognition. I would like to thank, of course, the members of the AI group at the Department of Information Engineering. And I just explained a little our work about federated learning at the Department of Information Engineering, but also the other department of the University of Pisa, the Department of Computer Science, is really involved in a lot of research about this subject with different solutions about explainability and also the proposal of some framework for federated learning, but this presentation was just to give the idea that this field is really explored in terms of the University of Pisa, and I think is one of the aspects we have that is interesting today to explore. I finish my presentation. I don't know if we have any questions.
I have a small question.
Yeah, okay.
A nice presentation about the last topic. And could you tell us something about configuration of client machines? Are there any limitation or specific requirements?
Oh, depends. I mean, when we have to cope with federated learning, we have just two possible scenarios. One is in a scenarios in which we have server as clients. So we have just big repository. We don't have problems in terms of limitation from a computational point of view or for a memory point of view. There is another scenario in which we really we have to cope, for instance, with sensors. And in this case, we have limitations, of course, in terms of computation and memory. These solutions we proposed are not really are not very problematic from the terms of computations. Because actually, especially for the solution in which we propose a decision tree in a federated way, we have just to compute only an aggregated information on the single clients. And normally this is not very expensive from a computational point of view. In terms of Shapley value, we have in any case a big problem because when you have to compute the Shapley values, normally you have to really spend a lot of computational time. This is the reason why normally we don't use the overall training set, but we use just samples of the overall training set. In any case, we also produce some framework for the federated learning. We just implemented one framework inside the European project, and we developed another framework now inside FAIR.
Thank you.
Yeah, welcome. Thank you for the question.